Hello. Our inspirational and motivational example suggests that also today we will look at algebraic equations that cannot be solved analytically, that is, using algebraic operations and similar tricks. And again, we will turn to numerical analysis for some tools that would allow us to identify approximate solutions of such, let's say, not very friendly equations. And what we did previously is that we took all these equations and we changed them in such a way that there was 0 on one side. So we move everything to one side, there will be 0 left on the other side. In that way, it transforms into a root-finding problem. However, algebraic equations can be written in many ways, and today we will prefer a totally different way of writing them, namely this one. We want to see x on the right. So when somebody gives us an equation, we rewrite it in this way, and then we have x on the right and some expression on the left. And again, this expression, that's the function that we will focus on. And we are not using f, we are using phi to emphasize that this is definitely not the previous approach with roots. Okay, this is a new situation. Now, we are looking for number x, which satisfies this equation. And when we think of phi being a function, we are actually looking for a very specific number. Let's have a look at a general mapping picture. So typically we would draw the starting set, the ending set, and then somehow suggest how the mapping acts, how it sends objects. Now in this case, the starting set will be real numbers typically, or a subset of it. So we have real numbers, a specific copy of real numbers, and perhaps there is some domain for the function phi. Then there's the target space, again another copy of real numbers. And now the function phi sends numbers from the starting set to the ending set in some way. We don't really know now because it's a general function phi. And we are looking for a very specific number, a number which has the property that when we put it into our function, which means we send it over, it stays the same. It gets sent to itself. And one possible interpretation of this situation is that the function phi is actually transforming the real line. We may have some objects here. Well, this is just a one-dimensional situation, so let's say we have some intervals there, and they make a nice picture. And then we take the function phi and we transform it so the picture changes. So phi is a transformation. And we are looking for special points that do not get changed by this transformation. They stay fixed. And that's exactly the name of this point. That's why there is this little subscript f. This means fixed. Let's have a look at the official definition. So we have a function, and we are looking for points xf so that when we substitute them, the output is exactly the same as the input. Now, the great advantage of this definition is that it's very general, and we will shortly show some interesting examples. So to appreciate what it does for us, let's have a look at some examples. Let's say here. So for the first example, I chose the usual square power. Very nice example, very simple. So how does it work? One copy of real numbers, another copy. Now here is 0, and let's say here is -2, and -2 is sent to 4, so it's somewhere up there. And 2 is also sent to 4. So there are all kinds of things happening. 1/2 is sent to 1/4, so it goes like that. And then we ask the question, okay, are there any numbers which are actually sent to themselves? Are there any numbers which stay unchanged when we apply this function to them? And that's actually a very simple question. The answer is yes, there are such numbers. One of them is 0, obviously, and the other one is 1. So 0 is sent to itself, and 1 is sent to itself. And we have two beautiful fixed points. Nice. Let's try another example. This time I'm going to look at the function square root of x. This will actually look at the first sight as the very same example regarding the, let's say, properties. Because again, we have two copies of real numbers, but actually this time I need not worry about negative numbers. So I will cut it off at 0. And the square root sends numbers in some way. Now it works differently. So for instance, 4 is sent to 2 and so on. And again, we ask, Are there any fixed points? And the answer is the same as before. Yes, 0 and 1. And I put them here. I put them here. And we have a nice picture for it. And you might ask, okay, why am I doing two examples that look almost the same? And the answer is, we will shortly see a difference. Now, the beauty of this notion, as I said, is that it's very general. When it says function, it can be real function, which is the usual meaning, but some authors interpret function in a wider sense. They actually think of a mapping when they say function. And we could try to play this game here. Mapping, that's a general notion. You have one set, another set, and you're mapping things. You're sending them over. Now, in this case, for a fixed point to make sense, those two sets, the starting set, the target set, they have to be the same. But other than that, there is really no restriction on what you are doing and what objects you are sending. So here is an interesting example. I have a mapping here which takes functions and sends them to some other functions. And how does it do it? It simply differentiates. Now here, one has to be a little bit careful. This is our starting set, and it's a set of functions, all kinds of functions here. And they are sent to their derivatives. So the target set is also a set of functions. Now what functions? Notice that it's not enough to take for the starting set the set of functions that have one derivative. Why not? Because the target space would have to be the same, but if you take a function that has just one derivative and you differentiate it, then the outcome does not have any derivative. So the outputs, they have one less derivative compared to the inputs, but I need the same space on each side. So this is a little trouble from calculus. This is not really a topic for this course, so let me just quickly say that one possible solution is to simply take functions that have all derivatives, derivatives of all orders, and then by differentiating you do not spoil this property. That's a very simple setup. But for us, the interesting question is, are there any fixed points? So let's translate it into another language. Are there any functions so that when you differentiate them, you get the same thing? Functions which are resistant to differentiation. That's a good way to put it. And the answer is, of course, exponential. Now, there is an interesting psychology that I really enjoy. I enjoy teaching, among other things, because it shows how people think, and this is sometimes surprising. Usually when I ask for a fixed point, everybody thinks of the exponential. There is another one, and it's also easy, and surprisingly, people somehow don't think of it. Yeah, it's not so easy, but of course you find that the zero function, the constant function 0, is another fixed point of the differentiation mapping. So this concept of a fixed point is something really general. Let me, as an illustration, I'm not going to work with it, but just quick illustration. You can take the set of all square matrices that are regular, and you can consider mapping, which takes a square regular matrix and sends it to its inverse. Now, does this mapping has a fixed point? Well, what do we expect? We expect the inverse to be the same as the matrix itself. Are there matrices like that? Of course, there are matrices like that. The unit matrix of some dimension, yeah, the identity matrix, it works like that, but there are more matrices. So in linear algebra or in matrix theory, they actually look at this, I think they call them involuntary matrices, matrices that work like that. So this is an interesting topic, and again, this is related to this notion of a fixed point. Okay, we have our fixed points in those examples, and that was nice, optimistic examples, but now let's have a look at another example. Phi x is equal to x plus 13. Is there a number which works in such a way that if you shift it by 13, you will get the same number? And the answer is not really. So this mapping, although it's very simple, it's a very nice linear function. It does not have fixed points. And of course, the picture is quite suggestive. This is just a shift by 13. So we cannot really expect to see any fixed points. So there may be fixed points, they may not be fixed points. Let's have a look at some interesting theory. Here is a very nice statement. Function is continuous on some closed bounded interval. That's an assumption because functions which are not continuous, they are troublesome. And it says that if the function maps specific interval into itself, then it must have a fixed point. So if this function that I have here in this picture mapped everything into the same interval, then according to this theorem, if this function is continuous, it must have a fixed point. That's interesting. Let's have a look at interpretation of fixed point from a different point of view, because we are not really used to treat functions like that, with this general picture. Instead, we prefer to look at their graphs. So how do we see fixed points in a graph of a function? Well, that's a good question. I have my function, phi x, and I'm looking for a number which if I put into the function, then the outcome will be the same. What does it mean? It means that this distance of the point that I'm looking for must be same as this distance of the image. And when you play with it, you should start seeing something. But let me help you with another point of view. When we have equality like that, we can look at the function on the left, we can look at the expression on the right and also treat it as a function. And then this equality actually tells us something about the intersection. So what we see here, the equation of a fixed point, is in fact equation describing intersection of my function phi, of the graph of the function, and a graph of the function given by the formula x, which actually is a linear function, and its graph is the diagonal, y equal to x. And this intersection should be the fixed point. Let's check. Over here, it's xf, and the intersection, it's actually something which is on the graph of phi. So over here, I can see the value of phi x. So it's here. This is phi x. But because this point lies on the diagonal, this and this distance must be the same. So this is also xf. Yeah, it's a fixed point. So that's the geometric interpretation of a fixed point. It's intersection between the graph of your function and the diagonal. And that's exactly the picture that we had for this equation when we started with it as an inspiration. So this is how I'm imagining that fixed points work for real functions. And let me go back to the theorem. The theorem says the following. I have a function, and there is some interval I. Let's say that it goes from a to b. And on this interval, there is this function phi, defined and existing. And now I'm assuming that the images of all points from here again lie in this interval. So I'm going to carry over this interval here. I think that could be it. So the image also lies in this interval, which means that the graph must lie in this square. There is a regular square which has the same interval for x and y projection. So it means that these 2 points, they lie on the diagonal. That's important. Because after all, the distance is a and a, b and b. So the graph of our function is somewhere in this square, and we are asking, is this graph intersecting the diagonal? Now, if the function is not continuous, then of course it may jump over. It may jump across this diagonal. So you can see continuity is crucial. But if this graph is continuous, then it must cross the diagonal, obviously. Well, let's have a look at the value at a. The value at a could be, again, a, and we have our fixed point. Or it may be something larger. So the value may be, let's say, somewhere over here. How about the value at b? It could be b again, and we have our fixed point. Or there is no other way, it has to be lower, let's say here. Now, if you have a continuous function which is passing from here to here, then whether it wants or not, it sooner or later must cross the diagonal. And you have your fixed point. There you go. Now, of course, this picture is quite suggestive, but this is not the proof. So for the proof, we have to do a little bit of work. We are going to introduce an auxiliary function, let's say phi x minus x, and let's talk about it a little bit. What do we know about this function? First of all, this function is continuous, because it's a difference of 2 continuous functions. Namely, it's continuous on interval I, which is ab. It's a bounded interval and it's closed. And because it's bounded, a and b are numbers, not infinities. Okay? So everything works as in the theorem. And now, let's see. Because the range of this function phi is again the interval AB, it follows that phi A must be at least A, which is the argument that we made over here in this picture. The value at A cannot be lower. What does it mean? Well, it means that h at A must be, and let's think about it, we are subtracting A, so we move it to the left, and we see this is positive. Here we go. Let's have a look at the value of phi at B. Again, by our assumption, this number phi B must be also in the interval AB, so it cannot be larger, definitely. We also know that it cannot be below A, but we don't care. The important thing is that it's less than or equal to B, which is what we used here in the picture. So we are actually translating the picture into algebra. If phi B is less than or equal B, I move B to the left, and I find that HB is less than or equal to 0. So now we have a function which is continuous, function h, continuous on the interval AB, and it's greater than or equal to 0 at the left endpoint, and less than or equal to 0 at the right endpoint. And there is something which is called intermediate value theorem, IVT, and it says that there must be some number, xf, in the interval I, such that h xf is 0. But hfx being 0 simply means that phi xf is xf. And we are done. So that's actually a very simple proof of our theorem. Yeah, this is actually shaping to be a nice lecture with proofs that are easy and complete. No cheating here. Perfect. So now we know that in many situations, functions have fixed points. But how do we find them? That's a good question. That's actually the main question of today's lecture. How do we find fixed points? And how do we do it efficiently? That's another good question. Well, there is an interesting idea. And it goes like that. We start with a specific guess. Okay, I will just say, okay, let's try some number, x0. And then I take this number and I substitute it into my function phi, and the output will be my next number, my next attempt to find a fixed point. And then I say, do I like x1? Is it a fixed point? I try it, and how do I recognize it? Well, actually, if I have a fixed point, then I have equality here between this point x0 and the point x1. If they are the same, I found my fixed point. If they are not the same, well, I apply phi to x1 again, and I get x2. And again, if x2 is equal to x1, I have a fixed point. If not, I keep going. Notice that x2 is actually phi of x0. So I'm repeatedly applying my function to my initial guess. I applied once, twice, 3, 4, 5, 6 times, 7 times, 8 times, 13 times, 100 times, and I'm waiting to get my fixed point. Or perhaps not. We will see. Let's try some experiments. Okay, let's go to my example with x squared, the function x squared. Let's say that I try x0 equal to 1/2. This looks like a nice number. So I'm going to apply function phi to it, which is x squared. And I get x1, which is 1/4, 1/4. Okay. Now I apply phi again, and I get x2, which is 1/4 squared, which is 1/16. And I apply phi again, and I get x3, which is 1/256. And I apply phi again, and I keep going. And, well, I think it's obvious where we are heading. I hope you can see it for yourself that there is no other way. This actually goes to 0, which is my fixed point. So this crazy idea of repeated application of the function phi actually seems to work for this example. Interesting. Let's have a look over here. Square root. I start with 1/2. Then I apply the function square root, and I get 1/2. Now, how much is it? That's a good question. Then I apply another square root, and another square root, and this is where it gets, let's say, a little bit tricky, because we have to call on calculus. In calculus, the limit of such a sequence is actually investigated, and it turns out that this sequence converges to 1. which is also a fixed point of our function. So for a different function, the same starting point took us to a different fixed point. This can happen easily. There is no reason why it should work the same way. After all, we have a different function. The important thing is that we did get a fixed point using this crazy idea. This is called iteration, fixed point iteration. And the general formula is like that. To get the next guy, you simply apply your function to the current guy. Okay? I think I wrote it as an algorithm. But the question is whether it's really worth writing it as an algorithm. It's so simple. Okay? Yeah, that's what it is. Iteration, fixed point iteration. How about this guy? How about this mapping which takes functions and sends them to their derivatives? How will it work there? Well, that's an interesting question. Let's start with initial iteration, which is, let's say, x cubed plus 13. Nice function. Okay, I'm going to apply my mapping, which is actually just applying the derivative. So I apply the mapping here, and what do I get is 3x squared, and that's it. Okay, I apply my mapping again. When I apply it, I get 6x. I apply it again, I get 6. I apply it again, I get 0. I apply it again, I get 0. And obviously this goes to 0, which is a fixed point of my mapping. It even works for such general situation. This is a mapping, abstract mapping, which sends functions to functions, and the fixed point idea, the iteration idea, actually works for it. So definitely there is something to this idea. It doesn't seem to be a blind alley. It works in many situations, or perhaps not. Let's see. Let's go back to my x square example. What happens if I start at 2? You may have been wondering about it already. So we apply, this time we're applying x squared, and we get 4. Then we apply x squared, and we get 16. Then we apply, we get 256, and you can easily see that we are going to infinity, which is not exactly the best fixed point. Now, okay, this is funny. When you square infinity, you again get infinity. So in a way, this is a fixed point, but not according to our definition. Our definition says fixed point must be something which is in the domain of your function. Infinity is not in the domain, so it's out. And this shows that there can be some trouble with convergence of this situation. But the great thing is, in all our examples, whenever we do get convergence, we also get a fixed point. And actually, this is true in general. So here comes another theorem. And this theorem says, if you have a function, this time it's a real function, we are talking with real numbers to get nice theorem, and we are defining sequence xk using the iteration that we have over here, using this formula. So we have a sequence which was generated, and if this sequence converges to some point, to some xf, and if phi is continuous, again continuity crucial, then we actually found a fixed point. Now, the square function, the square root function, the cosine function when we are at it, these are all continuous functions. So if we try this iteration and it converges, it must necessarily, according to the theorem, provide us with a fixed point. Now, how do we know that this theorem is correct? Well, we will prove it again. This should be enough. Let's see. We have a sequence xk. What do we know about it? Well, it came from this iteration. So xk plus 1 is phi xk. Now, that's an equality. In fact, that's infinitely many equalities. It's equality between two sequences. So I'm going to apply limit to each side. Limit of xk plus 1 is limit of phi xk. Can I do it? The answer is yes, if the limit makes sense, if it exists. Let's talk about it. What do I see on the left? Limit of xk plus 1. xk plus 1 as a sequence is the same sequence as xk, just the index is shifted. So graphically, I have some dots, sequence xk, and I shift it. So if there is a limit for xk, there must be also a limit for the sequence xk plus 1, and it's the same. I think there was a theorem like that in calculus. So this limit on the left is actually the same as limit of just xk. And we know that this limit exists from our assumption, and therefore also this limit exists. So we were right to do this thing. Let's have a look on the right. This is a composed situation, and for composition we had a theorem again in calculus. And the theorem said, if this function phi is continuous, then it can be pulled out of the limit in a way. Algebraically, it works like that. Instead of applying limit to phi xk, I can apply phi to the outcome of the limit. Now, we are there. Limit of xk is supposed to be some number xf, and the same number is appearing as an argument of the function phi. And therefore, this limit point xf is a fixed point. Exactly what we wanted, a small square here. So that's another neat proof. We didn't really need any deep theory for it, just few facts from calculus. Very nice. So what do we know? We know that if you have a function, then of course it maps one interval into another because it goes from real numbers to real numbers, but this is not enough. According to the theorem, we are interested in bounded intervals. This is where it gets interesting. So for some functions, you can find a bounded interval which is mapped into itself. And if you get this lucky, then definitely there will be some fixed point. Is that true for our example called cosine x? Well, that's an interesting question. We know that the outcome of the cosine is always in the interval -1, 1. So it makes sense to look at a cosine as a function which takes the interval -1, 1 and maps it into the interval -1, 1. So according to this previous theorem, this must have a fixed point, the function cosine. And this fixed point is actually the solution to our original equation. How do we find it? Well, we try to apply this iteration business, and if it converges, then it will provide us with the answer. Now, when I was young, the computers were really rare. It was difficult to get to them, but everybody had a calculator. This iteration is actually very cute because you are just repeatedly applying your function to the number that you have. So I could actually do this iteration on a calculator with cosine. You just pick some number at random, you put it into calculator, and you press the button which is labeled cosine, and you get x1. And then you press the button again, and you get x2. So you just keep pressing the button, and you're looking at the numbers and asking, okay, are they going to converge somewhere? Does it look likely or not? And that's actually the whole secret. Let me mimic this with Maple. For starters, I will take, let's say, number 1. That's a nice number. I like it. And we know that the fixed point is somewhere between -1 and 1, so why don't we start at 1? Now, I take this x, and I'm going to apply cosine to it. And this will become the new x, because I want to iterate. So this looks like a mathematical equality, but it's an assignment. On the right, it's the old x, and on the left, it's the new x. And then I can just repeatedly run this line, and this simulates the process of just punching the cosine again. Okay, let's see. Forgot. Maple is trying to be smart, so it refuses to calculate numbers which can be kept precise. Okay, so I'm going to force Maple now to do it imprecisely. And cosine of 1 is 0.54. Notice, remember, 0.4. Now I will press the cosine button again on my calculator. And the next number is 0.85. So 1, 0.5, 0.8. Up, down, and up. This is interesting. So I expect the next number to be down. Let's see. 0.6. So it was 0.5, now it's 0.6, 1, 0.5, 0.8, 0.6. It's a zigzagging motion which is getting more and more narrow. Let's repeat it a few more times. So I keep pressing the button cosine on my calculator, and these numbers are getting closer and closer together, still jumping up and down. I did it already like 10 times. So this is cosine of cosine of cosine of cosine of cosine of 1. Okay? And it seems that the first decimal digit, 7, is no longer changing. And this looks hopeful because it suggests that perhaps I will have some convergence happening. And now 0.73 is no longer changing. And now 0.739 is no longer changing. So this really looks like a convergent sequence, the one that I'm generating here. So it seems that for cosine, this iteration business works really well, and it provided me with an approximation of my solution of this number x that I'm looking for, and I think by now the 4 decimal digits should be okay. So this looks like a good procedure, and we actually have most of this procedure supported by mathematical statements, with one key exception: convergence. The theorem says if your iteration converges, then it provides you with your fixed point. But how do we know? How do we recognize convergence? How can we arrange for convergence? That would be even better. And for that, let's revisit our example over here. Let's start with the square root of x. What do we know about the function square root of x? Well, if you put into it a number which is larger than 1, then the number will get smaller. And if you put still larger number, it gets smaller, and so on. So in this upper part, the arrows go downwards. And actually, the higher go, the more steeply they go down. On the other hand, if you substitute a number which is between 0 and 1 into the square root, it gets larger. So here we have some arrows that go like that. Now, why is this interesting or important? Let's think a bit more about what the iteration does in this kind of a picture. So here we go. I have the starting space, I have the target space, and now I have some x0. That's my initial value which I just dreamed up, and I put it into the function phi, and it gets sent to some x1. Now, in the next stage of my iteration, I should take this x1, which I obtained from phi, and use it as an argument. So what I need to do, I need to transform this x1 back into the original space. So I have to go like that, horizontally, so to speak, to get to the same position, x1, and now I can substitute it into phi, and phi sends it over to x2. And again, then I have to transform it to the original space, and I keep going. So this iteration, fixed point iteration that we have here, this is actually something like a spiral, or let's say merry-go-round. We keep going from one space to another like that. In this direction, we are using phi, and in this direction, we are going horizontally. That's how the iteration looks like in our arrow picture. Now let's have a look at what's happening here. We start at some place, or let's say we started at 1/2. We started at 1/2, and when we go to the right, we go up. And then we go back horizontally, and we go up, back horizontally. So it seems that we should be going to number 1, just by looking at the arrows. And that's exactly true here. What if we start with a number which is larger than 1? Then it gets smaller by applying the square root. We return back to the original space, and we go to the right to a smaller number, and so on. So this is a spiral which, again, should lead us to number 1. And you can check if your x0 is, let's say, 2, you apply square root, and you apply square root, and you apply square root, and so on. And again, in the calculus, we learned that this is actually a convergent sequence going to 1. So this seems to work. The important thing is concentric arrows. They are forcing this merry-go-round to get to some place. How about x-square function? Well, if we take a number which is between 0 and 1, and we apply square to it, it gets smaller. So there are arrows going towards 0 here, and therefore when you start this business with 1/2, this spiral will take you to 0. This looks, reasonable. This fits with our experience. What happens if you start with a number which is larger than 1? Well, there the arrows go up. So when you are going around and around, you just fly away, and you get divergence. So this experience suggests that the cases of concentric arrows are good, and the cases of arrows which are spreading out, fanning out, are not really good. So it's all about concentration of arrows. Is the function viewed as an arrow picture concentric or spreading out? So there must be a notion which somehow captures it. And if we can develop mathematical theory about this notion, then we seem to have a good chance to succeed in identifying convergence. And that's exactly what's going to happen right now. Here we go. This is a definition of a so-called contraction or a contractive mapping. And this is actually supposed to be the mapping which is like concentric, which is moving numbers closer together than they are at the start. And that's actually reflected in the inequality. So we have some interval. On this interval, we have our function phi. And now we take 2 points at the starting space. We look how far apart they are. That's the right-hand side. We move them over, and we check how far apart the outcomes are, the images. And then we want the images to be closer compared to the original points. That's the inequality here. Now notice that Q is required to be smaller than 1. That's very important. Let's have a look at a small picture. What would happen, and I think this is sort of natural, if I just put this inequality in the definition. This means that the images are always closer than the original points. Over here, I have x, I have y, and they get closer together. Phi x, phi y. But if I leave it like that, and I put, of course, this for every x, y from I, then it may happen that as I'm taking different pairs from the interval I, that the distances between images are getting closer and closer to distances between these two pairs. So this inequality may be getting softer and softer, closer and closer to equality. And because there are infinitely many pairs in any interval I, if it's non-degenerate, then I could be actually in a limit achieving equality. And if I have equality in limit, it would spoil all kinds of things. So I have to prevent this possibility that some pairs of points have almost equality. And that's why I have to introduce here another constant, a separation between this distance and this distance. I want to see real separation. I want to see real concentration by some specific amount. So this Q, it says it's the worst that can happen. That's the worst sort of like spreading out that I can see in my situation. And it definitely should be smaller than 1. Okay? So that's just a technical explanation. So here we have contraction, that's the key notion. And now comes a key theorem. It's a celebrated theorem, it's called after Banach, so it's important. When there is a name in the title, then it's an important theorem. And this is, in fact, the key theorem for the whole theory of fixed points. And you can find it even in very advanced mathematical courses. I will talk about it soon. Let's see what it says. We have an interval. And on this interval, we have a function which is contractive. Moreover, this function phi maps this interval into itself. And then there is exactly one fixed point. And it can be reached using iteration. So when we define a sequence xk using this iterative formula, then this sequence converges to our fixed point. So let's have a look at the proof. It has several parts. First of all, it says that there is a fixed point. How do we know? Well, if the function phi is a contraction, then it must be continuous on interval I. How do we know? Well, one has to prove it. This is not really difficult. You look at the definition of continuity, you will see it there. In fact, it's even uniformly continuous. There is some theory about it in calculus. So this is really not a big problem. Just to give you some idea. If a function is not continuous, then it may have a trouble typically of this sort. It can get worse even. Now, when you have a situation like that, then you have 2 points which are really close, but when you substitute, the images are far. So any type of discontinuity automatically violates this principle of concentric arrows. Okay? So I think this is not really a proper mathematical proof, but I think it makes this statement believable. So we have a continuous function, and moreover, it maps interval into itself. That's another assumption, line 2. And therefore, by previous theorem, there must be some fixed point. So we have it. Great. That's step 1. We do have a fixed point. Step 2. It says there is a unique fixed point. Just one, cannot be more, for contraction. How do we prove it? Well, let's imagine that we have 2 people, and each of them brought a fixed point with them. One says, okay, this is a fixed point. Another one, this is a fixed point. And now we want to show that these 2 guys independently actually had to come up with the same fixed point. They cannot have 2 different fixed points. So let's ask about the distance between these 2 fixed points. Well, here is a trick. I'm going to apply the function phi to each of them, and the trick is that this is a fixed point, so xf is actually the same as phi xf. I don't have to use any specific justification, anything crazy, some facts about absolute value or anything. I am simply replacing a number by the same number just written in a different way. The same argument applies to phi x tilde. And now I look at it and I say, wait a second, phi is a contraction, so there is an inequality which goes like that. I can simply drop the phi again in exchange for q, which is less than 1. That's important. We will see it soon. Now, I have an inequality. Let's say that I take the right-hand side and I move it to the left. I subtract from each side, and I factor out this distance. So I'm getting 1 minus q times this distance is less than or equal to 0. Now, let's have a look at this. That's a distance between two numbers. This is always greater than or equal to 0. Q is less than 1. So this number is positive, a strictly positive number. If this absolute value were positive also, then positive times positive yields a positive number, which is in contradiction with this inequality. So the only way to make this inequality work is to have the distance between these two guys equal to 0, so they are actually the same. End of step 2. We just proved uniqueness. Perhaps I should put the conclusion somewhere. It's an important part of the proof. That's what we wanted. So, it seems that no matter what you do, there is just one fixed point, and we are finally getting to the stage where we simply pick some initial number, some initial guess, and we generate the sequence xk plus 1 and so on using the familiar formula, using our fixed point iteration, and now we have to show that this actually converges to xf. And I will do it by essentially deriving the left inequality, the left estimate, and then I will look at it. So, how much is xf minus xk? I will just use a slightly different notation because it will make my life a little bit easier. Well, let's have a look at it. xf can be replaced with phi xf. We talked about it earlier. This is a fixed point. We know it now. xf is a fixed point, unique one. xk, by definition, is phi xk minus 1. Now, because I have a contraction, I can use inequality with q and drop the function phi. xf minus xk minus 1. So that's exactly the type of inequality I had been interested in. I just shifted the index by 1, and you will see the reason why. Because once I have this inequality, I can continue by induction. So, assuming that this number, this index, is not 0, which it could be, so assuming that it's not 0, I can again apply phi to each and so on. I simply recycle this inequality, and I get q squared xf minus xk minus 2. And then I keep going like that. How many times can I afford to do it? And the answer is essentially k times. And this requires a little bit of thinking, not too much. And after you repeat this k times, you get to x naught. For instance, if k is equal to 1, then after one step you get to to x0, and you have one q here. Okay, so this all fits nicely. So, I have a nice inequality here. On the right, I have an upper bound for this number, which is actually the error of approximation. Remember, I have my fixed point, I'm trying to approximate it, and I found that this, which is the error, because we can see the difference between the actual value and my approximate value, the error is bounded by q to power k times the initial error. Now, what do we know about q? Q is less than 1. It's a positive number smaller than 1. So in absolute value, q is definitely less than 1. And therefore, this, as a geometric sequence, goes to 0. So the error goes to 0. There you go. This shows that my sequence converges because the error goes to 0. xk converges to xf. And that's the most important part of this theorem, that iteration actually works for contractions. There is another inequality, which is essentially just out of curiosity. It's proved by doing the first step and then playing with it a little bit. Not too crucial. What it shows, by the way, is that on the left, we still have this error. And on the right, we are just using the latest two iterations. So the information on the right, that's something that we know from our run. And if we also know Q, then we can actually estimate our error and stop in time. So this is nice, but actually in applications, we very often do not know Q. And then there is a trouble. Okay? So the Banach fixed point theorem is crucial for this whole theory because it says once you have a contraction, everything works perfectly. And you can even choose x0 in any way. You just start somewhere in the interval, and your iteration will work. By the way, when you look at the comparison of errors, this is the error for the kth step, this is the error for the k minus first step, you get this. Let me shift the index again so that it looks familiar. This actually shows that the fixed point iteration is a method of order 1, which is not exactly all that great, by the way. But we will soon talk about ways to fix it, to speed it up. So this is actually not so bad. The main advantage of the fixed point approach is that it can be used in general settings. This Banach fixed point theorem is also true not just for numbers, but also in other sets, in other spaces. For instance, we had this example of a mapping which was differentiating functions. We talked about its fixed points here and so on. Well, actually, you can introduce the notion of a distance between two functions. And once you have the notion of a distance, you can start talking about contractions. So you can ask whether this differentiation map is a contraction or not. And if it turns out that it's a contraction, then by the Banach's fixed point theorem, actually, you get the existence of the fixed point and you get this iteration working because the Banach's fixed point theorem can be proved to be valid for any space in which you can measure distance reasonably well. So this is an extremely general and extremely powerful theorem. But we will not really look into it here because we are interested just in real numbers. Okay? Talking about real numbers, we have real functions. How do we recognize whether they are or they are not contractions? That's a practical question. Somebody gives a formula. Do we really want to do estimations like that, comparing, trying to figure it out? Of course not. So what to do instead, you look at the requirement with Q here, and you rewrite it in a different way. What do I want? Well, I want phi x minus phi y divided by x minus y to be less than or equal to q. That's what I want. And I also want q to be less than 1. When I look at the left-hand side, of course I have a feeling of déjà vu. I saw this one before. Of course, it reminds me of the mean value theorem. So we know that there must be some psi, traditionally written, which if I substitute it into the derivative, it will give me exactly this ratio. So this is what I want. It's not equivalent, by the way. It may happen that I do have a contraction, but for instance, it need not have any derivative at all. This can happen. So the information doesn't flow this way. It floats this way. If I have a function and I find that the derivative is bounded by some number smaller than 1, then using the mean value theorem, it follows that all these ratios also have to have this bound. So the information flows in this direction, and that's exactly the direction that I want. Because for me, it's much easier to investigate the derivative than investigating some ratios. Let's put it up. So this is a theorem which essentially follows just from calculus. And the proof is more or less here, and that's what we are going to be using. Let's go back to the Banach fixed point theorem and apply it to our motivational example. Cosine x is equal to x. So we're looking for a fixed point of the function cosine, and we found it. Let's support it theoretically. First of all, we need some interval which the function cosine sends to itself. And we talked about it. The natural candidate is the interval -1, 1. which is sent to negative 1, 1. So far, so good. So we have interval I, which is sent to itself. Then we have to also show that the function phi, cosine, is a contraction there. So let's ask about the derivative of cosine. How does it look like? Well, the derivative is sine of x. And we are interested in the magnitude. What do we know about sine of x on the interval negative 1, 1? That's the key, negative 1, 1. Well, on interval negative 1, 1, and this is a little bit important, so let's think about it for a second. How much is 1? Is it more or less than pi over 2? Pi is 3 point something, pi over 2 is something like 1.6 whatever. So 1 is definitely smaller than pi over 2, which is somewhere over here. And how does the function sine look like? It's equal to 1 here at pi over 2, then it goes down, and like that symmetrically. And because it's an increasing function, when we put it in absolute value, it becomes like that. We can claim that sine of x in absolute value is definitely bounded from above by sine at 1. And from the picture, it is obvious that sine at 1, that will be RQ, is less than 1. So we do have a contraction. The function cosine is a contraction on the interval negative 1, 1. And therefore, according to the Banach fixed point theorem, our business with iteration will definitely work. And it did work. So this theorem is the main tool for the fixed point iteration. And as a theoretical tool, it's wonderful. But there are some, let's say, practical complications. First of all, when somebody gives you a function and it's not really friendly, then it may be difficult to establish an interval which is going to be sent to itself. For a complicated formula, it's not easy to analyze what's happening to intervals when you're applying this function to them. So that's one practical problem. And in such a case, we very often use just an inspiration from this contraction business for local information. We know from this that actually flat functions are good for iteration. Because small first derivative, it means the function is flat. It may be increasing slightly, decreasing slightly, but not too fast. That's the whole idea. So the general message is that we like flat functions. But the problem is once we start playing with it locally, we can no longer rely on Banach fixed point theorem formally. So the information that we get is not guaranteed. Rather, it's advisory. We will see this in examples. The second thing is, or the second factor to keep in mind is that the Banach's fixed point theorem is just an implication. So there are also other situations when the iteration works, even if the function is not in contraction. So it's not exhaustive. If we just focus on Banach's fixed point theorem, we may be missing on some other good cases. A lot depends on configuration. So let me show 4 typical examples of what can happen, and we will see it better. Let's start with the square root example. So here's the diagonal, a very important feature, and here is the square root function. But for now, I will actually not worry too much. Now, our first task is to actually develop understanding of what the iteration does in this type of a picture. Now, we talked about interpretation of this fixed point iteration in the arrow picture, that we are going like that, a merry-go-round. How do we see iteration in the graph picture? Well, here we go. We have 2 spaces, x and y. This is the starting space, this is the target space, and now we choose x0, so let's say that it's here. We have to find x1 by substituting this into phi, which we do just by looking it up like that. We go vertically up, and we find x1. So far, so good. But now we have to take this x1 and transform it into the x space so that we can use it again as an argument. How do we get this number here? We need to find the same distance to get to x1. Well, there is actually a trick. We are going to use the diagonal, y is equal to x, to use mirroring to transform this distance here. And we do it like that. From the point on the graph, we moved to the left to get to the y-axis and find x1. But now we go back to the right, all the way to the diagonal, and then move down. And because this diagonal creates symmetric shapes, this distance and this distance, they must be the same. So really, x1 is now determined by going through the diagonal. Okay, we're sitting here. What do we do next? We have to substitute x1 into phi. So we go up again, all the way to the graph, and then we go left, and we get x2. But then we have to transform x2 to the x-axis. So we go to the right again, all the way to the diagonal, and then we go down to get x2. And then we substitute x2, so we go up again, all the way to the graph, left, right, and so on. Now you can see that some of the journeys were actually useless. They were not contributing. Here we were going left and right again. Here we were going down and up again. Left, right again, down, up again. All these journeys which are outside of this shape were useless. We can just focus on the movement inside this shape. We were going up to the graph, to the right on the diagonal, up to the graph, to the right to the diagonal. So the substance of iteration, as I see it in the graph picture, is like that. You go up to the graph of phi, and you go left or right, depends on the situation, to diagonal. And this is the geometric interpretation of our iteration. And it works. Let's have a look at it. What happens if the starting point for our iteration is here? This may be also x0. You go up to phi, which will lead you over here, and then you go horizontally to the diagonal. And this is actually a shortcut for two trips. One of them is here to get x1, and then you go to the diagonal and back to get x1, to this position. So here is x1, then you go vertically to the graph of phi, and you notice that it's not up but down. So this is really vertical movement. This is key. Vertical movement to phi, horizontal to diagonal. Horizontal to diagonal, vertical to phi. Horizontal to the diagonal, vertical to phi. And you can see that we have convergence also here if we start on the right. So from this picture, it seems that the function square root of x is very kind to iteration, because it doesn't matter where we start, we eventually, in this zigzagging motion, get to the fixed point, which is over here, xf. And we actually saw this in the arrow picture. They were concentric, all pointing to fixed point, which is 1 actually. So that's the situation for the square root. Let's compare it with the situation for x squared. Here is the diagonal, and here is x squared. How does it work here? Well, we choose some starting value, x0. Actually, this is not the right place for it, x0. And then we are supposed to go vertically to the graph of our function, and then horizontally to the diagonal. Then we are supposed to go vertically to the graph of our function, so we go downwards, and horizontally to the diagonal, and so on. And it seems that we are converging to 0, and that was exactly the case in our experiments. If we started between 0 and 1, here is 1, the fixed point, then iteration seemed to be going well. Now, let's have a look at it. The iteration is going well in the places where our function is flat. Also here the function is flat. So flatness seems like a good idea. What happens if we start iterating at a place where the function is not flat, where it's steep? Well, if we start here, then we go up to the graph, then we go horizontally to the diagonal, up to the graph. Well, there must be a way here, then to the diagonal, then up to the graph, and so on. You can see the divergence easily. Okay? So let's say if I start somewhere closer, then perhaps I can make a few steps here that are visible. So let's say that I start here, and this will be x1. So up, horizontally, and so on. So this shows that when the function is really steep, then we are in trouble. And this actually works also for decreasing functions. These were increasing functions of different flatness. Let's have a look at a decreasing example. For a decreasing example, I can actually borrow our motivational example over here, cosine function. That's a nice function. So how will it work here? cosine is relatively flat, around 1. That's the function cosine. But it need not be cosine, just any function which is decreasing and relatively flat. Well, okay, we will pretend that this is still decreasing, but with horizontal tangent line. What happens if I start with, well, over here? Picture will be better here. If I start over here. Well, I have to substitute into my function, which brings me here. And then I have to find the value and use the diagonal to transform it to the x-axis. So I go horizontally to the diagonal, and this will be my x1. Then I go vertically, because I'm substituting into phi, I go to cosine, which is up here. And again, I go to the y-axis, and then using the diagonal, I transform. So I'm going to the right, in fact, to the diagonal, and this will be x2. It seems that my journey is getting closer and closer to the fixed point, but notice that this time I'm not going monotonically. Here x0, x1, x2 was increasing. Here it was decreasing. Here it was decreasing. But here I'm jumping left and right of the fixed point. And this is typical for decreasing functions. So when the function is increasing, the sequence which you generate will be monotone. When the function is decreasing, it will be alternating around the fixed point. So that's an interesting observation. Now, generally, we like monotone sequences, but when it comes to convergence and to estimating what's happening, actually this alternating business is, let's say, more interesting because you can see where it goes much better. So when phi is decreasing, you get alternating. And we also saw that when phi is flat, then you get perhaps convergence, and when phi is steep, you get perhaps divergence. This is for sure, this is most likely, okay? We cannot rely on that completely. We will see soon. So that was the case for cosine. We got this nice jumping left and right of our approximations. This is exactly what we saw in Maple when I was playing, pretending to be a calculator. Okay? And you can see that graphically, instead of a stair, which we can see over here, so instead of stairs, we have something like a spiral, which is winding inside inwards towards the fixed point. What happens if you have a function which is decreasing and steep? So that's the last case. A steep decreasing function could be going somewhere. Okay. Is it steep? I guess so. So let's have a look at the situation. And quite frankly, I may have overdone it. So, yeah. Okay, let's see what happens. x0, just to the right of the fixed point. I go up to the graph, and I end up here. Then I go horizontally to the diagonal. So that's the first true step. The step from x0 is always preparatory, but afterwards I just move in my graph. Okay. Horizontally to the diagonal, vertically to phi. Horizontally to the diagonal, vertically to phi. Horizontally to the diagonal, vertically to phi. Horizontally to the diagonal, vertically to phi, horizontally to the diagonal. Well, you can see the message. Again, there is a spiral happening here, but it's unwinding. It's going away from the fixed point because the function phi, which is over here and over here, is steep. So this really seems to fit with the general picture that we have with the general feeling. The Banach contraction theorem or the Banach fixed point theorem says if you have a contraction, if your function is flat, you can expect nice things. So actually this line is okay, more or less, based on the Banach's fixed point theorem. This line is not quite 100% true because, square root example. Notice that the graph of the function square root is quite steep over here. In fact, the derivative is approaching infinity. But still, on the range between 0 and any number you care to use, you can start anywhere here, and the iteration will always take you to the fixed point 1, unless you start at 0, and then the iteration gives you 0. Okay? So over here, in this area, iteration actually also works and leads you to a fixed point, even though the function is not flat here and it's not a contraction here. Definitely not. So this is a nice example that the configuration plays an equally important role as the, let's say, geometric properties of the graph. Okay. So this makes this whole fixed point business a little bit more challenging, because you don't have just one tool, but one has to sort of look at situations, think about it, and essentially what you can simply do, you try it. When you have a situation that you do not see, you try iteration, and if it works, you say, okay, great. I don't have to worry why it works. I'm just happy that it worked. Okay? So that's the general setup. And that's essentially it regarding the fixed point iteration. We have the whole theory done, and we have some interesting examples, and we have a very good insight into what's happening. Now, let's pass to another good question. Can we somehow make this iteration go faster? Let's erase the blackboard.